This week I've come to Abu Dhabi in the United Arab Emirates to see a building that's not that high, just 160 metres, with not that many floors, just 35, containing nothing that interesting, just offices and a hotel. Unremarkable by any standard. However, it is in the Guinness Book of Records. And this is the reason why. This building has an 18-degree tilt to the west, which is almost 5 times more than the Leaning Tower of Pisa. The only difference is, this one is on purpose. This is Capital Gate, also known by the locals as the Leaning Tower of Abu Dhabi. It was developed and is owned by the Abu Dhabi National Exhibition Company, which runs the adjacent exhibition centre and, interestingly enough, Excel, the exhibition centre in Docklands in London. Construction started here in 2008 and it opened its doors in 2011. The building is mixed-use commercial, including offices, retail spaces, and in the upper floors, a 5-star hotel. The hotel in Capital Gate is a part of the Hyatt Group, and as you can imagine in a building like this, has a very modern feel to it. It has 188 rooms and suites, together with all the normal amenities like a gym, spa, a swimming pool, and a restaurant and bar. The rooms are modern, light and airy, and each one has a totally different shape because of the unusual shape of the building. My room is almost at the very top and in a part of the building with the biggest overhang. So little do you realise when you're at the window taking in the views of Abu Dhabi that just a couple of floors below you is fresh air. But I'm not here to talk about the hotel or the view out the window, but to answer the simple question, how does a building like this manage to stand up with such a massive lean? You see, the forces on this building are absolutely massive. Firstly, the overhang caused by this 18-degree lean is not small by any means. From the base to the furthest point out is 33 metres or 108 feet, which is absolutely enormous and the reason for the world record. And the forces, because of this lean, are quite staggering. If we look at the part of the building that overhangs the ground floor, the part that's doing its best to pull the whole thing over, it's substantial and weighs quite a bit. However, it is quite easy to approximate how much this is. Let me show you. I've done a very rough calculation and it comes to approximately 1 hotel. Yes, just about all of this overhang is the 188 rooms of the hotel accommodation, together with some of the public areas. All of this is outside the footprint of the building and it's trying its best to pull the building over. To make it easier to visualise just how much this is, we can actually change the units from hotels to houses, if that makes it easier to comprehend. So with this amount of wonk on the building, that's an engineering term, how does it manage to stand up without collapsing? Well, any building that's actually leaning has got 2 main ways it can fail. If it's strong enough, because of the lean, it will want to rotate and potentially any foundations it's got will want to be pulled out of the ground, a bit like a tree pulling its roots out of the ground when it goes over in the wind. Failing that, most buildings won't be that strong, a bit like the Leaning Tower of Pisa. If that goes, it's not going to pull the foundations out, it's just going to break in half. So what stops Capital Gate actually snapping like a twig? Well, let me show you on a very rough and ready model of Capital Gate that I've knocked up, because there's things within the building that you don't see from the outside that gives it the necessary strength to stop it collapsing. So this is Capital Gate, 35 stories high with a helipad on the top, and halfway up on the non-leaning side is a swimming pool that's a part of the hotel that occupies the top half of the building, the bottom half being offices. But the reason it doesn't break in half is actually on the inside. Because what you don't see within the structure is a reinforced concrete core travelling the full length of the building. In construction of tall buildings, we use concrete cores like this to give lateral or sideways strength to literally help stop buildings falling over, normally called a lift core. Because on modern buildings they're so important, they're normally constructed ahead of the main building, and sometimes on a large building site you can see them sticking up ahead of the main construction, just like on this site that I came across in London. And as the lift core in this building is doing more work than the average building, as you can imagine, this core is quite big. Depending on where you are in the building, depends on how many lifts are going up and down, because some of them only go to the offices at the bottom. The core at the bottom contains 11 lifts, plus voids for services to go up and down, plus a couple of emergency staircases as well. But this core, quite literally also, has a twist to it. You see, because of the lean of the building and the off-centered load, it literally pulls the building over to one side. So if the lift core was built straight on day one, by the time the rest of the building was complete, it would be pulled out to vertical by around 350 millimeters or 14 inches. So the engineers predicted this. So to get around the problem, they built the whole lift core pre-cambered out of plumb. So as the building was constructed, and all this weight on the right hand side gradually came on, it pulled the lift core absolutely vertical like it is today. Now that is quite clever. So the lift core essentially takes the whole weight and the rest of the building hangs off of it. Although some of the loads in the bottom half of the building are being transferred down into the ground, the majority of the upper floors are transferring all of their load straight into the core, and not like in a standard building where it's common to have perimeter columns helping to share and spread the weight away from the core and into the ground. So to get the loads from the rooms and the restaurant into the core, what sort of framework makes this, well, work? Now the strength, shape and structure of this hotel is made up of something completely different to most buildings. It's called a diagrid, and that's these big beams that you see behind me. A diagrid is a series of triangles joined together a bit like a lattice, making it a very strong but lightweight framework. You can spot these sometimes when you're out and about if you know what you're looking for, a bit like the roof over King's Cross Station or the structure of the Gherkin building in the city. In the top hotel section of the building, there's two of these diagrids, one on the outside of the building made up from 600mm or 2 foot square steel box sections, and one on the inside made from hollow round sections, forming an atrium in the shape of a funnel, letting in natural light from the skylight at the top. The structure of each floor is then suspended in between the inside and outside diagrid. This atrium is really impressive and runs from level 35 at the top down to level 19, so really only half the building, although I'm sure most people staying in the hotel and looking down will probably think that what they're seeing at the bottom is somewhere near ground level. However, you still have another 19 floors below this before you get anywhere close to ground. These diagrid structures then transfer all the loads to the core and are all over the building, and once you notice them, you see them everywhere around the building and they become a feature of the internal decoration, which I like. Hanging off the external diagrid is then another more lightweight frame supporting all the glazing on the facade. And this glazing is made up of 26,000 triangular panes, which are designed to be able to move up to 20mm each to allow for the building to expand and contract in the Arabian heat. Anyway, given the fact that the building is strong enough not to snap in half, the second way it could fail is by simply overturning. Because of the overhang, there is a huge overturning or rotational force trying to rotate the structure and pull the foundations out of the ground. To help this building stand upright, it's sitting on a massive reinforced concrete raft, which in turn is sitting on about 500 piles. So the other thing that no one appreciates because they just can't see it is the building is sitting on a massive foundation of just under 500 piles. Now these aren't the type of piles that are hammered into the ground like a lot of people think. These are columns of reinforced concrete, 600 millimeters to a metre in diameter, somewhere between 20 and 30 metres deep, that have been augured out with a big piling machine and then filled with concrete and rebar, essentially making a big, long concrete column. But on this building, they're not all working in the same way. You see, at the beginning of construction, when the building was still quite low, all of these piles sitting on the piling cap were all in compression. That means they're all being pushed down because you've got the weight of the building here. But as the building increases in height and this lean comes on, the whole thing wants to tip to the left. What you find is the piles on the left hand side are in compression, but the ones on the right hand side are actually in tension. They're locking down the pile cap to the ground. They're pulling the building back to earth and stopping that rotational force that gravity is doing its best to pull the building over with. And they only do that simply by friction between the concrete of the pile and the soil or the rock around it. A bit like concreting in a fence post and then trying to pull it out of the ground afterwards. You'll find it's fairly tough. And in this situation, it's just exactly the same, but on a bigger scale. So with all these clever engineering solutions in place, Capital Gate, although still being the wonkiest building in the world, is safe and secure and quite simply one of the best engineered buildings ever. There's no doubt that to design and fabricate a curving, almost random shaped building like this is only possible in the modern day with the use of CAD and 3D modelling. However, that computing power, I think, only enhances the basic principles and good design practice the structural engineers that worked on this already know. And in the case of Capital Gate, it's amazing what they've achieved that once again isn't immediately obvious to the passing public. I hope you've enjoyed this video. If you have, please remember to subscribe and hit the bell notification button so you don't miss future episodes. I will see you next time.